Hi, my name's Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to introduce matched molecular pairs in MOEsaic. This is a search algorithm that finds compounds that differ by some substructure. MMPs are important to SAR analysis because they can detect both activity cliffs and bioisosteric replacements. So let's get started. Here we've got a preloaded dataset that will optimize for COX-2 activity. We're using the default view with an overview of the dataset with filtering options on the left-hand side. We have a reference pane for pairwise comparisons and a global view of the dataset in the middle, and then finally property analysis using models and plots on the right-hand side. There are three different methods to exploring MMPs in MOEsaic. We have interactive MMPs for visual inspection of a reference structure, MMP profiling to query a transformation of interest, and then finally interesting MMPs for global MMP exploration. Let's start by looking at interactive MMPs, which we can initiate by clicking the MMP button that sits in the footer of the reference. And notice when I hover over different parts of the ligand, they become highlighted in green, showing us what we call the variant structure, the part that changes between two or more structures in the dataset. In the background, this is leveraging the fragmentation that was performed when we first launched MOEsaic. We can invert this so that we could look at the invariant, the part that's not changing. So for example, if I click on this pyrazole, it will return all structures that contain the pyrazole together with their respective R groups. So I can go back and explore other MMPs. I'm just going to clear this search, and for now I'm going to focus on the variant. And when I do that, you notice that the three hydrogens are displayed here on the reference. Think of these as variants displayed on our reference, indicating that there are related compounds in the dataset that differ at that position. As an example, if I click on this hydrogen, it returns both the reference together with an analog, which is identical, with the exception that a hydroxyl is replacing the selected hydrogen. Using the properties pane, I see that these compounds are generally similar in terms of the properties, with the exception of COX-2 activity. So an example of an activity cliff, a small change in structure leading to a drastic change in activity. In this example, we used MMP to investigate the impact of different R group substitutions or terminal groups on activity, but we can also use it to investigate the impact of different cores or scaffolds upon activity. And you notice that we have these red arrows indicating the relative positions of fragments or substitutions from other structures within the dataset. I can use these to isolate part of the structure that I want to query. As an example, if I want to include both of these substructures, I can use the red arrows to carve out the portion of the molecule that I'd like to go ahead and query. So I'm just going to clear that for now, and going back to the earlier pyrazole example, where we found all structures that contain that substructure, I'll do the same search, but this time in the variant mode, to see what else is found in this position with the same R groups. And I'll just click this, and when I do that, it returns the reference together with an analog, which is identical, with the exception that that pyrazole is replaced with an imidazole. Looking at the properties pane, I see that we found a bioisostere, so perhaps useful to break a pattern. Now, having seen this one bioisostere, a common resulting question would be, can we always expect to see a bioisostere when that pyrazole gets replaced? To answer the question, we can't just query this one reference. We need to query the entire dataset, including all of the fragments that were generated when we first opened the session. So for that, if I just clear this search, I'm going to perform an MMP profile, which opens a sketcher, which allows me to sketch the transformation or replacement of interest. I have different atoms and bonds so that I can do my sketch, but I also have these shortcuts, and I'm just going to click the last MMP variant, and I'm going to use this as my starting position to just copy and paste that to the other side of the transformation, and then I'll just manually cycle my nitrogens and then click search. So this opens a new tab, and we see the pairs of structures from the database that have the same R groups plus the transformation that we just sketched. Note that we're no longer looking at a reference pane. This is a matched pair pane, so we just get the left and the right variant, and the structures pane becomes a table. We see our invariant, the R groups, and the transformation that we sketched together with the impact on activity. Each line of the structures table is represented by a pair of connected dots in the plot pane. So we've got X plotted along is our invariance, and Y would be our COX-2 activity, together with a key that shows us that green dots represent the pyrazole, red dot for the imidazole. So here it's quite easy to identify several instances of bioisosteric replacements where these dots are either on top of each other or nearly on top of one another. But there are examples of this same substitution having quite a drastic change in terms of activity. Furthermore, sometimes it's the pyrazole that's more active, sometimes the imidazole. So we can use MMP profiling to query a specific transformation, but we can also use it to profile the desirable groups at a given R group position. So I'll just go ahead and use MMP profile again, and this time I'll use our reference structure, and I'll just remove parts of the ligand that I don't need for this specific query, and then I'll add in my R group. But this time I'm going to leave the right-hand side of the transformation blank so that I can query all of the other fragments found in that position. So the structures pane is by default sorted by delta COX-2 with the positive values that sit all the way at the top, indicating that we've got some R1 groups that are more potent than the tolerable. I want to dive deeper into our original reference structure, so I'm just going to isolate that specific core of interest, and I'll just invert that selection. And then I'm going to plot on our x-axis S log P as a measure of hydrophobicity. So points to the left of the central reference point indicate that we've got compounds or fragments that are less hydrophobic than the reference. Any points that you see above would indicate that they are more potent. Now, to focus in on those transformations that are more potent, I'll just use our filters pane and set the lower bound delta COX-2 to be 0, so that we only find different fragments that actually improve the activity. So our references here, and as I say, anything to the left would be less hydrophobic, but we can also think about adding in other properties such as molecular weight. So we saw how to compare two specific structures using the interactive MMP search and how to query the entire dataset using MMP profile. But these examples are driven by an original reference structure. What happens if we don't have a reference, or we simply want to ask to see the most interesting pairs of structures? So for that, we can consider interesting matched molecular pairs for a global analysis of our dataset. And this opens a panel which allows us to define what constitutes as being interesting. Here we're optimizing for COX-2 activity, so if I wanted to find some bioisosteres, I'd perhaps change the absolute change in field value to be close to 0, or I could have a look for activity cliffs, but I'll set mine to be somewhere in the middle, looking to improve the activity. I'm going to set the number of heavy atoms added or removed to be 0, so that we can compare compounds of a similar size. And notice that we can generate quite a few hits with this algorithm, so for that reason we might want to consider making our query a little more specific if we do reach that ceiling. So the view that we get, it's in a new tab, Interesting MMPs, similar to the MMP profile tab, but since we didn't query a specific group, there are different left and right variants corresponding to the most drastic changes in activity. The structures pane is ranked according to delta COX-2, the parameter that we defined as being interesting, and this first result therefore exhibits the largest change in activity, and we see the pair of structures that are responsible for that. So making the substitution that is shown here has this impact upon activity. In this case, both of these have the same number of heavy atoms. So I can scroll through to have a look at the different pairs of structures and their respective impact on activity, and you'll notice that some of these are grouped. So we've got 4 compounds here which are grouped together because they have the same invariant but different left and right variants. I can just go back to the full data set by clicking back there. And I just want to mention in the filters pane that by default we're only seeing single R group MMPs and single invariants. So I'm just going to add in another filter here. I'm going to add in the delta S log P so that I can find compounds that have similar properties. So I'll just put in minus 0.2 and plus 0.2 so that we find pairs of compounds with similar properties but a different structure. And that brings us to the end of today's session, where we explored MMPs in MOEsaic to identify activity cliffs and bioisosteric replacements. We used interactive MMP for visual inspection of a reference structure, MMP profiling to query a transformation of interest, and then interesting MMPs for global MMP exploration. If you have any questions, please do reach out to us at support@chemcomp.com.